Is time travel possible in your opinion? I don't know what you think, but there are many people who don't seem to be joking about it and claim to have traveled in time. Some of these individuals claim to have worked for the government and to have been chosen as a soldier for a time travel project. Some say they traveled back and forth to a date 4 years in the future due to encountering a strange weather phenomenon. Others insist that they were sent from the year 2005 to the distant future of 3000.89973 during a secret mission for the British government. In my opinion, all of these are fabricated stories. Many people tend to agree, but does that mean time travel is impossible? Let's take a look at this phenomenon from the perspective of scientists. Many science fiction novels written in the past have explored various themes such as submarines and trips to the moon, which over time have transitioned from science fiction into scientific reality. So why shouldn't time travel become a reality one day? Indeed, time travel is not just something possible in the future. There are individuals who are already traveling into the future today. For instance, Russian cosmonaut Sergei Krikalev is arguably the greatest time traveler in human history. Holding the record for spending the most time in Earth's orbit, Sergei spent a total of 803 days, 9 hours, and 39 minutes in space, effectively journeying into his own future, albeit only 0.02 seconds ahead. He experienced what is known as time dilation, traveling at speeds of up to 28,000 kilometers per hour. But how did this happen? And more importantly, what happens when we go to even higher speeds? According to Einstein's theory of special relativity, when you approach the speed of light, an object begins its journey through time. For objects moving at relatively low speeds, such as the International Space Station, we wouldn't observe this effect, or if we did, it would be extremely minimal. We'd need to go much faster, around 300,000 kilometers per second. To better understand this, let's consider an example. Let's say we have a spaceship capable of traveling close to the speed of light. The owners of this spaceship are twin siblings named Jesse and John. Jesse serves as the pilot of the spaceship, embarking on a year-long galaxy tour while John remains on Earth. Jesse returns to Earth, having aged biologically by 1 more year. All the clocks and time-measuring devices on the spaceship agree that a year has passed since leaving Earth. During this journey, John observes Jesse for a year and learns about the peculiar effects of Einstein's theory of special relativity caused by Jesse's near light-speed travel. According to John, time on the spaceship appears to pass slower than on Earth. If John had a powerful telescope capable of seeing the spaceship, he would perceive everything in slow motion. Clocks would tick more slowly, and Jesse's movements would be sluggish. However, from Jesse's perspective, everything would seem perfectly normal. Hence, the 1-year journey for Jesse aboard the spaceship appears to be 10 years for John on Earth. Indeed, when Jesse returns having aged 1 year, she finds that her twin brother has aged 10 years. Of course, the values I provided in this example will vary depending on the speed of the spaceship. The closer we get the spaceship to the speed of light, the more time will pass on Earth, according to Jesse. In fact, when the speed becomes exceedingly high, 1 day for Jesse could be equivalent to thousands of years on Earth. This means that upon her return, not only might she fail to recognize her twin brother's 10-year-older self, but she might even struggle to locate his grave. However, all of this doesn't explain why and how the passage of time changes according to the theory of special relativity. We all remember the formula speed equals distance divided by time from school. Here, let's have the speed represent the speed of light, which I mentioned earlier to be approximately 300,000 kilometers per second, or roughly 1 billion kilometers per hour. Now, there's an important point you should know. This speed of light is constant for all observers and doesn't change in any way. It's crucial to understand that this was experimentally confirmed back in 1887 by 2 scientists, Albert Michelson and Edward Morley. Years later, Einstein came along and had the final say with his theory of special relativity. No matter how you move relative to each other, the speed of light is the same for all observers. Now let's go back to the formula speed equals distance divided by time, and try to explain why traveling at high speeds means time travel. Using an example, imagine I'm here on Earth, and my assistant has lit a beacon in the sky. I transform into a version of Superman and start moving away from Earth in the same direction as the light, at 3/4 the speed of light. Let's say when my assistant measures it, the light is moving away from me at 1/4 my speed. Now, what do you expect to see when you look at the beam of light passing by me? Logically, you would expect to see the light moving away from me at 1/4 of my speed, right? In other words, I should see it moving away at a speed of 250 million kilometers per hour, just like my assistant observed. However, because Einstein insisted that every observer measures the speed of light as the same, I should also see the light moving away from me at a speed of 1 billion kilometers per hour. That is, at the same speed it had when it left the beacon. But how could that be? It doesn't make sense. When the light left the flashlight, it did so at a speed of 1 billion kilometers per hour. But if I see it at 1 billion kilometers per hour divided by the hour, something must have happened along the way. And my speed of 750 million kilometers per hour must have been added to the speed of light, making the light's current speed 1,750 million kilometers per hour. But what did we say earlier? The speed of light doesn't change in any way. Light remains unchanged. However, it covers much more distance than I do. According to the formula, speed equals distance divided by time. If the speed remains the same while the distance is different, it means that the elapsed time must be different. So the only way this can happen is if my time passes more slowly than it does for those on Earth. Yes, indeed. Even with the construction of a hyperspacecraft capable of reaching such high speeds, it still seems almost impossible today. However, the largest experiment proving time travel in a sense has already taken place at CERN in Geneva, Switzerland. Scientists there accelerated particles in a circular tunnel beneath the Earth's surface, making the particles orbit around the tunnel nearly 11,000 times per second, which is almost equivalent to the speed of light. When this happened, the particles began to travel through time. They observed this through extremely short-lived particles called p-mesons. These particles normally decayed in just 1/1,000,000th of a second, but then they found that when they reached speeds close to the speed of light, p-meson survived 30 times longer. The only way they could achieve this was if time was slowing down for them. Therefore, we can conclude from Einstein's theory of special relativity that one of the consequences of the constant speed of light is that time slows down at high speeds. Now, what about general relativity? Let me introduce you to the second way of traveling to the future. With general relativity, there's another way to slow down time through gravitational pull. You can slow down time using the gravitational effects of massive objects. What Einstein noticed with his theory of general relativity is that matter drags time with it and causes it to slow down, much like the slower flowing part of a river. This astonishing fact is the very thing that provides the possibility of traveling into the future. In the center of the Milky Way, 46,000 light-years away from us, lies the heaviest object in the galaxy. It's a supermassive black hole where 4 million solar masses are squeezed into a single point by its own gravity. Now imagine you're approaching this black hole. The closer you get, the stronger the gravitational pull becomes. If you get too close, even light can't escape. A black hole like this would have a dramatic effect on time, slowing it down significantly compared to everything else in the galaxy. This essentially turns it into a natural time machine. Imagine, as I mentioned earlier, that Jessie jumps onto her spaceship, and this time, she enters orbit around the black hole. While John observes from Earth, he would see each complete orbit taking 16 minutes. However, Jessie on the spaceship, exposed to the gravitational pull of the black hole, would experience time passing at half the rate. For every 16-minute orbit, she would only experience 8 minutes. This means Jessie is moving forward in time. After spending 5 years in orbit around the black hole, when she returns, 10 years would have passed on Earth. So far, I've told you a lot of things. We've gone at the speed of light, turned into Superman, had Jessie board a spaceship for intergalactic travel, and hung out near black holes. But when Jessie returns to Earth, can she go back to her own time if she doesn't like what she sees? Time travel to the past. Let's dive into it. That's where the real challenge lies. Traveling to the future poses no problem. But when it comes to traveling to the past, things get complicated in an instant. This is because going to the past means causing a slew of paradoxes. To tackle this issue that gives physicists headaches, I'd like to start with a very familiar example, the grandfather paradox. For instance, if you were to travel back in time using a machine and killed your grandfather before he met your grandmother, what would happen? Your mother would never be born, and consequently, you wouldn't exist either. However, if you didn't exist, you couldn't kill your grandfather. So, you leave your grandfather be, and he goes on to meet your grandmother, and you are born. Now, you can go back in time again and kill your grandfather. This seems to go on infinitely. At first glance, it appears that you cannot kill your grandfather because doing so requires your existence. It defies the first law of thermodynamics. Physicist Jim Al-Khalili, whom we are accustomed to seeing in documentaries, made an important observation about time travel. He pointed out that using a time machine violates the law of conservation of mass and energy. How so? Let's say you use a time machine to go back 5 minutes in time. In that case, you would have two versions of yourself simultaneously, and you would introduce extra mass into the universe. However, there is no extra energy available to account for the sudden appearance of this additional mass. You have violated one of the fundamental teachings of physics, which states that something cannot be created from nothing, thereby breaking the first law of thermodynamics. Some have proposed the idea that time travelers cannot intervene in past events, only observe as spectators to avoid this inconsistency. But look, what does Khalili say about this? This view is akin to going back in time and entering a movie, where you can observe events without being seen by others. Although it may seem to create paradoxes, this passive form of time travel is unfortunately even more impossible. In the real world, nearly all forms of interaction between two objects involve electromagnetic interactions that include the exchange of photons at a fundamental level. If light photons can enter your eyes and allow you to observe the past, then everything should be possible. In other words, if we can see something, it should also be possible to touch it. Then we need another method. One of the weirdest yet most valuable ideas to emerge from theoretical physics in the last century may solve this paradox. The idea of parallel universes can make time travel possible for both the future and the past. According to this hypothesis, our space-time contains only one of the infinite futures and infinite different pasts. Time traveling to the past in a multiverse is no different from going to the future. Just as there are many possible futures in front of us, there are many possible pasts to visit. Time travel means following a time loop that leads to one of these possible pasts. So, according to the theory of parallel universes, you can now go to a new universe where you can kill your grandfather. If you give birth in that universe, it's a done deal. The theory of parallel universes even eliminates the problem of the conservation of mass and energy, because now you consider preservation across all the multiple universes, not individually. You, as mass and energy, move from one universe to another. Thus, the total mass and energy of the entire multiverse remain unchanged, but a minor issue may arise. With so many parallel universes, you might never find your way back to your original universe again. The topic of parallel universes has been a subject of curiosity in physics and a staple of science fiction for decades. To date, there has been no experimental evidence to prove the existence of parallel universes. Traveling to the future seems much more feasible than traveling to the past. However, this does not necessarily mean that the theory of parallel universes will never be proven. I guess this topic deserves its own video. So, how about discussing parallel universes in the next video? For now, farewell. As for me, I'm just a lonely human, and I hope to see you in a new research.